Across the universe, astronomers are finding planets that should not logically exist. According to classical models, extreme radiation, gravity, or temperature should destroy them quickly, yet they remain stable for billions of years. These discoveries force scientists to rethink how planets form and survive. Instead of neat systems like our solar system, the galaxy is filled with chaotic environments where worlds endure conditions far beyond theoretical limits. Some planets orbit so close to their stars that a year lasts only a few hours. Their surfaces glow hotter than molten lava, and their atmospheres boil constantly. Solar winds blast them with radiation strong enough to strip entire oceans in minutes. Still, gravity binds them together. These ultra-hot worlds behave like cosmic experiments showing matter can survive far more energy than scientists predicted. On certain exoplanets, metals evaporate into the air. Iron becomes vapor, rises into the atmosphere, cools on the dark side, and falls as molten rain. Imagine a storm where droplets glow orange before hitting the ground. Such weather systems redefine what a climate can be. Instead of water cycles, these worlds operate on mineral cycles, proving planetary environments are not limited to Earth-like chemistry. Rogue planets wander between stars with no sunlight at all. They should be frozen lifeless rocks, yet some emit heat signatures. Internal pressure and radioactive decay warm their cores, possibly sustaining underground oceans. Entire ecosystems could theoretically exist beneath thick ice layers, protected from the vacuum of space. These lonely worlds suggest life might not require a star at all. Brown dead stars called neutron stars, planets somehow formed after violent supernova explosions. The original blast should have erased every nearby object. Instead, debris gathered into new worlds orbiting intense radiation fields. Their skies would glow with lethal energy constantly. If observers stood there, atoms in their bodies would disintegrate instantly, yet the planets themselves remain stable. Scientists also found planets less dense than foam. They are larger than Jupiter but weigh surprisingly little. Their atmospheres stretch far into space, barely held by gravity. Stellar winds should disperse them quickly, yet they endure. These superpuff planets challenge our understanding of atmospheric physics and show gas behavior on cosmic scales differs dramatically from expectations. There may be diamond planets made mostly of carbon. Under immense pressure, carbon crystallizes into structures harder than any natural material on Earth. Mountains could sparkle like gemstones under alien skies. Lava there might flow as thick black carbon melt. Entire landscapes would appear metallic and reflective, transforming geology into something closer to jewelry than rock. Some planets orbit two stars simultaneously. Their paths curve unpredictably as gravitational forces pull in competing directions. Early simulations suggested such orbits were unstable, yet many have survived billions of years. Their surfaces would experience multiple sunrises and shifting shadows daily. Seasons would never repeat in the same pattern, making climate extremely complex but surprisingly stable. Water worlds may contain oceans hundreds of kilometers deep. Pressure at the bottom forms exotic forms of ice hotter than boiling water. Above lies endless ocean with no land anywhere. Waves could rise kilometers high under strong gravity. Without continents, chemical cycles differ entirely, suggesting life, if present, would evolve in ways unlike anything on Earth. Some planets orbit magnetars, stars with magnetic fields trillions of times stronger than Earth's. The magnetism can reshape atoms themselves. Chemistry changes because electron paths distort. Materials behave differently, meaning matter there could have properties unknown in laboratories. These environments show physics remains consistent but manifests in unfamiliar forms under extreme conditions. There are worlds older than many stars around them. They formed when the universe contained few heavy elements. According to theory, rocky planets required later generations of stars. Yet these ancient planets exist, meaning planet formation began earlier than models predicted. The timeline of cosmic evolution must be longer and more complex than assumed. Some planets spin so fast they flatten into ovals. Gravity nearly loses its grip at the equator, where objects could weigh far less than at the poles. Winds circle continuously, forming permanent global storms. Despite instability, they remain intact, demonstrating rotation can stretch planetary structure without destroying it. On tidally locked planets, one side faces the star forever while the other stays dark. Temperatures differ drastically, yet atmospheric currents transfer heat efficiently. A narrow twilight band may host stable conditions. This region could maintain liquid water even when the rest of the planet is frozen or burning. Planets have also been detected forming from the ashes of dead stars. After a star collapses into a white dwarf, Leftover material forms a disk. Gravity slowly gathers debris into new worlds made of heavy metals. These second-generation planets prove planetary birth can occur even after stellar death. Some systems contain planets orbiting backwards compared to their star's rotation. Their origin suggests violent gravitational encounters in the past. Despite chaotic histories, they settle into stable paths. This means planetary systems may rearrange dramatically over time rather than remain fixed from formation. All these discoveries share one message: the universe is stranger than imagination. What once seemed impossible repeatedly becomes reality. Each world expands the limits of physics as we understand it. Rather than breaking natural laws, they reveal how incomplete our knowledge still is. Space does not follow expectations. It follows deeper rules we are only beginning to uncover.